Right, ladies and gentlemen, let's continue with chapter 4, now in the textbook of White. It is part of the fluid mechanics work, and in this chapter we derive the continuity equation, the momentum equation, the energy equation, etc. And the reason we do it is because it is part of convective flow and also convective heat transfer. So it connects to heat transfer, and it's also a very important building block to your CFD course, so that you know exactly what is happening on the inside in the CFD. Right, so with the previous lecture, we've derived the continuity equation. Today we're going to derive the differential equation for linear momentum. Okay, the momentum equation. And again, let's start with control volume, because remember, it is differential equations, okay, not the integral approach. So there is our control volume. Our coordinate system is that Z, okay, that is X, and that would be Y, and those distances would be dx, dz, and dy. Okay. And when we look at momentum, our, let's call it elementary knowledge of momentum is that it is the mass flow rate multiplied by the velocity. Okay. So if we now look at the momentum entering that phase, then the mass flow rate we can write as the density multiplied by the velocity, and the velocity would be in the x direction, so it would be equal to u, and it will enter into the phase dy dz multiplied by the velocity. Okay. The mass flow rate is equal to the density multiplied by the velocity in the x direction, in this direction, multiplied by the phase through which it enters, multiplied by the velocity vector. Okay, so in terms of the velocity vector, obviously it will have components u, v, and v in the x, y, and z directions, just as we've done yesterday. So if we now just go back to the force balance that was done in chapter 3, where a control volume was considered, the equation, the momentum equation looked like this. The sum of the forces would be equal to partial ddt of the integral over the control volume of the velocity vector multiplied by dv. Take note, this v is the volume, plus the sum of I of the mass flow rate in multiplied by the velocity out minus the sum of I, the mass flow of the velocity, the mass flow multiplied by the velocity in, and let's call that equation 2, because equation 1 would be the continuity equation.
Ask if anyone had it in a phone here.
So what about her?
Phone.
A phone?
Phone.
A what?
A cell phone.
A cell phone. Anybody a cell phone that you found? Where was it approximately? Anybody? Okay. If you guys can just look if there's a cell phone, please assist her and see if you can get it, if it's there. Okay, ladies and gentlemen, let's continue. Okay, so that would be equation 2, and equation 1 would be from the previous lecture is the continuity equation. Okay, so again, because it's a small element, we would like to take this term and say that this term, we can say it is equal to partial ddt of the velocity vector multiplied by rho and dx, dy, dz. I think there must be a density there. Okay, there must be a density there. So the velocity vector multiplied by the density, the volume, now is equal to dx, dy, and dz. Just as we've done with the previous lecture. And it can be written then, just a little bit more neat, as partial ddt of rho multiplied by the velocity multiplied by dx, dy, and dz. And this will now be equation 3. Okay, just like with the continuity equation, let's see what is going in and what is coming out in the 3 different directions. So direction and what is coming in and what is going out. Okay. Now in the x direction, we've said that the momentum flowing in would be equal to rho multiplied by u multiplied by the velocity vector v multiplied by dy dz. And as we've done the differential approach with the previous lecture, where we've looked at the simple equation, what happens if you want to see, you make an approximation of a straight line change, you use the gradient multiplied by the starting value, and then you can predict what would the value be at the outlet. We do exactly the same. And when we do it, we just make it a little bit more neat, and the result would be just like yesterday, rho u multiplied by the velocity vector plus partial ddx of rho u v multiplied by dx and then dy dz. And the same in the y direction and the same in the z direction. Okay, you can go and write it out at home. But that is typically how it now looks. So now we take equations 3 and 4 and we put it into 2. So equations 3 and 4 into, equation 2. Equation 3 and 4 into equation 2 in this one here. This, obviously that term, everything going out, everything going in. And in terms of, that is the equation. Okay. So the result would now be the sum of the forces would be equal to partial dt of rho v multiplied by dx, dy, and dz plus everything coming in, okay, and everything out. Okay, it's not very neat, but principle.
So you don't have equation 4 on the board?
This is equation 4. Equation 4. Okay. Happy? Okay. Okay. Now again, you will see that this part and that part is going to cancel. You see, rho uv multiplied by that, and the result would be only that term there, and it would be in the x direction, the y direction, and in the z direction. So this equation can now be written as the sum of the forces is equal to, and once you've made it a little bit neat, it's equal to dx, dy, dz multiplied by partial ddt of rho v plus partial ddx of rho uv plus partial ddy of rho v plus partial ddz of rho w multiplied by the velocity vector. Okay. dx dy dz is equal to partial d dt of rho multiplied by the velocity vector plus partial d dx of rho u in the x direction multiplied by the velocity vector, d dy rho multiplied by v, small v, multiplied by the velocity vector, plus partial d dz of rho w multiplied by the velocity vector. Okay. Okay. You can go and do it at home, take your time, but if you go and look at this equation carefully, it is actually equation 1, which is the continuity equation. And that part is equal to 0. Okay. So the result is that the sum of the forces is just simply equal to partial d dt of rho multiplied by the velocity vector multiplied by dx dy dz. Okay, so now if we look at this, we will say, well, sure, we are very fortunate. This momentum equation, the result of it is a very simple thing, but that is not it. That is just one part of it. Okay, the sum of the forces actually, we just said the sum of the forces is equal to that. And what we now did is we've calculated everything that happens on the right-hand side, which is equal to that. We still need to look at the sum of the forces on a control volume. Okay. Now, the forces that work on a control volume, there are two kinds. And I hope you can still remember it from your fluid mechanics course of last year. The first kind is body forces. Body forces, and the second one, surface forces. So body and surface forces. Okay. Body forces, which body forces do you know of in fluid mechanics? First one, gravity. Okay, so gravity in mechanical engineering is the one that we normally work with. Okay. Then there are others that we do not normally work with, like, for example, external electrical fields, magnetism, electrical potential, and stuff like that. Okay. So you need to know that there are forces like that, because if you use a CFD package, computational fluid mechanics package, you have to realize you have to go back to the equations and correct it if necessary, or you need to take it into consideration. Okay. Right. Surface forces has to do with stresses on the sides of the control volume. Okay. And there are different types. There are hydrostatic ones and there are viscous ones. Now let's just quickly, before we look at the surface forces, just look at the gravity one that we know very well. Okay. So the gravity one, okay, so the gravity force, normally in terms of our coordinate system, X, Y, Z. In the fluid mechanics course, we normally work with gravity in the negative Z direction. Okay, negative Z direction. Okay, so the result of that is that if we look at a control volume and we would be interested in the gravity force on it, then it would be equal to rho multiplied by its mass. Let's just write it like this. Sorry. Okay, the mass multiplied by g. Okay, and the mass is equal to rho multiplied by dx, the volume, dy dz, multiplied by g. Okay, so that would be the gravity force. The mass multiplied by g. The mass is equal to the density multiplied by the volume multiplied by g. Okay, happy with that? Right. Now, let's look at the surface forces here, at the surface. Okay. And if you have a control volume, and take this control volume and draw it quite large, it would help you a lot. So also make it a little bit large. And then you put in the coordinate system very carefully. X, Y, and Z. Okay, X, Y, and Z. Okay. Now there are 18 forces on the surface. On every one of these surfaces, there are 3 forces. Okay. A normal one, and 2 to the side, shear ones. Okay. And the numbering of them can be very complicated. I don't know if you've done it, but can also be very simple if you follow a few simple rules. Okay. Now, what I would suggest you do is you would take this surface and you would put the vector on it. Then that one is defined as x, as sigma xx. Okay. Okay. This one would be sigma yy, okay, and that one would be sigma zz. Okay. Right, now once you've done that, you can draw in the others like that. And always in the x direction. And then it's very easy. You put in there sigma x. Okay, so the first value would be the x. Okay, this one would be in which direction? Oh, sorry, that one. It would be in the z direction. This one would be in the y direction. You follow? You happy? Looks as if you do not agree with me or not happy. Happy? Okay. Okay, now obviously if your z-axis in this direction or y-axis in that one, like I've done there, then it will be different. Okay. So whichever one you follow, just make sure of that. Okay, now that one would be in that direction and it would be in that direction. Okay, you agree? So that one would be sigma z and also sigma z. That one would be in the x direction and this one would be in the y direction. Okay. This one, like that and like that. Okay. Sigma, the first one, indicates the y, like that, and the second one indicates the direction. So that one is x, and that one is z, like that. Okay. So it looks very complicated, but what is important to always remember when we look at these stresses is it is not the values of the stresses that causes the force, but the differential that causes the force. Okay, so the values from this surface to that forces would actually cause the net force on the volume. Right. Now, so what we now then need to do is you need to look at this control volume like that. Okay, now let's just look at it from that direction. And what we now do is we need to look at these stresses on the surfaces or the forces. Okay, so if it's now the x direction, then this one would be sigma xx multiplied by dy dz. Remember that would be equal to dy, and dz would be in the direction of the board, that is the surface on which it works. And taking into consideration that differential approach, then we can also say this one would be that plus the gradient and everything multiplied by dy dz. Okay, and we have to do it on all the surfaces, on all of them. And then we will say that the sum of the forces would be equal to rho g, okay, minus the grad of the pressure plus the grad of tau ij is equal to rho multiplied by dv dt. Okay. So that would be all the pressure forces working on the control volume. I can understand if you feel a little bit lost now. Obviously, it takes some time and quite a number of terms that you need to put into this to get it. Okay, now let's look at every one of these terms. Term 1, term 2, term 3, and term 4. Okay. Now, term 1 represents the gravity force. Gravity force per unit volume. Okay. Gravity force per unit volume. Okay. Term 2 would represent the pressure force per unit volume. The pressure force on the control volume. Okay. Term 3 would be the viscous force. The viscous force per unit volume, and term 4 is just the density acceleration per unit volume. So that is what each one of those terms will represent. Okay, now what makes these things difficult or complicated, well, not really complicated, just lots of terms if you work through all the detail, is that you now need to go and look and determine what those are. Okay. Now, but before we do that, let's just look at, if you go and do this now for the equation and you just look at the result in the x direction. Okay, so if we look at the x direction result only, because we just do not have time to write it out in the y directions and in the z direction, then the result would be the equation looking like this: rho multiplied by gravity minus partial rho dt plus partial tau xx dx plus partial tau yx dy. If you wonder where does the taus now come from, it's not the sigmas, they are taus, and I'm going to explain it to you just now. Okay, plus partial tau zx partial z is equal to rho multiplied by partial du dt plus u multiplied by partial du dx plus v partial du dy plus w partial du dz. Okay, so that is, if you go and write out everything, then that should be the result in the x direction only. You'll get a similar equation in the y direction and in the z direction. Okay, now before I explain to you these terms, that would represent actually the shear forces on a surface. Okay. And the very special case when we say we want to consider flow which is frictionless. Okay. If it's frictionless, then the viscosity is equal to 0, and then tau ij would be equal to 0. So all three these terms would be equal to 0. Okay. Now that special case, if that is so, is called the Euler equation. Okay, the Euler equation. So if we make this equal to 0, then we end up with the Euler equation. Okay. Now this equation was also the equation that was used to derive the Bernoulli equation. So that was the first assumption that was made. Okay, viscosity is equal to 0. And then after that there were many more assumptions. Bernoulli equation is about the equation with the most assumptions that there is in fluid mechanics. Okay, viscosity is 0, density is 0, one-dimensional, irrotational, etc., etc. Many assumptions. So when you start making things 0, then and steady state, etc., then you're going to end up with a Bernoulli equation. But firstly, if you say that is equal to 0, and that would be a valid assumption for many cases, then you will end up with what we call the Euler equation. Okay. Now in terms of these shear stresses, you've done it in terms of special fluids. Again, a Newtonian fluid. Okay. Newtonian fluids for us in engineering is very important because it says that the shear stresses is directly proportional to the viscous or the strain rate, du dz. And there will be a linear relationship, and that gradient would be equal to the viscosity. Now, for us in mechanical engineering, most of the fluids that we fortunately work with, air, water, etc., are actually Newtonian fluids. It is just when you start working with the blood, okay, or plastic materials at a high temperature, then they are non-Newtonian fluids. And you need to know it because you cannot then make the assumption that we are going to make now. So for those cases then, you can say that tau xx would be equal to 2 times the viscosity multiplied by partial du dx, typically, and tau xy is equal to mu multiplied by partial du dy plus partial dv dx. Okay, so the sigmas, okay, to the taus, you have to go and work through this, and then you're going to end up with relationships like this that will give you typically these types of equations. And it will also be that tau yx would be equal to the same. Okay. Then you need to put that all back into here and then make the equation neat. Okay. So when you've done that, or even before you do that, you can say, well, this is a lot of work. Let's make things even more simpler, and we do that by saying that the equations that we're going to derive now are called the Navier Stokes equations. The Navier Stokes equations. Okay. Okay. So in the derivation of the Navier Stokes equations, there are two very important assumptions. The first one is it is for a Newtonian fluid. Newtonian. Okay. And the second one is that the viscosity is constant. Constant viscosity. Because it is possible that the viscosities in the three different directions might differ. And the third assumption is it's incompressible flow. Incompressible flow. And then the result would be that the Navier Stokes equations can be written as follows. Rho multiplied by gravity in the x direction minus partial dp dx, okay, plus the viscosity multiplied by partial d2u dx squared plus partial d2u dy squared plus partial d2u dz squared is equal to rho multiplied by du dt. Okay. So that is now the Navier Stokes equation in the x direction. Okay. So take note, there's the x to indicate it's in the x direction. It is the pressure gradient in the x direction, then the second derivative partial to the velocity in the x direction, which is u, and again we want to see how u changes as a function of time. Okay, you've got the equation. The y direction, the same thing. Looks like this now. Rho multiplied by g in the y direction minus partial dp, that now not to x but to y, plus the viscosity multiplied by partial d2v dx squared. It is now in the y direction, so it's the v velocity, plus partial d2v dy squared plus partial d2v dz squared is equal to rho dv dt in the y direction. Any questions? Try to write it down in the z direction also. Do it in the z direction quickly and see if you can do it. Sort of just need to follow the recipe in terms of the y's and the x's and the z's. Okay, let's do it in the z direction. Rho multiplied by gravity in the z direction minus partial dp dz plus the viscosity multiplied by partial d2v dx squared plus partial d2v dy squared plus partial d2v dz squared is equal to rho dv dt. Okay? So, the Navier Stokes equation, and this would typically be the equations that you start with the CFD course in terms of discretization. Now you know where it comes from. Okay? What is very important, ladies and gentlemen, it's not the results of, obviously, the results are obviously very important, but you need to understand where it comes from and all the assumptions that were made to get to that. Okay? So that when you have very special applications, you immediately know that you cannot use the Navier Stokes equation. You have to go back. For example, let's consider you interested in designing a new aeroplane, Mach number of 10. Can you use the Navier Stokes equation? Is it valid? No, why not? Because at a Mach number of 10, flow is not incompressible anymore. Okay, normally at Mach numbers smaller than 0.3, flow is incompressible. Okay, larger than 0.3, compressible flow. Okay, if you consider a flow situation where you want to solve the heat transfer and fluid flow through somebody's heart, okay, then you work with the blood. Blood is not a Newtonian fluid, so you have to go back and you have to go and correct the equations. Obviously, it makes them much more complicated, but then, only then, you'll be able to get a right answer. Okay, that was the derivation of the momentum equation. The next one is the derivation of the energy equation. Okay, 4.5. Differential equation for energy. Now, we're not going to write down everything. I'm just going to start and then I'm going to give you the result. Okay, so just to start with, to see where it comes from the fact that we look at a heat flux, Qx. Okay, now what is a heat flux again? Let's just come back to the heat transfer rate, which would be equal to the heat flux multiplied by the surface area, and that would be in watts. Okay. The heat flux would be equal to the heat transfer rate divided by the area, and that would be in watts per square meter. So the heat flux is just the heat transfer per square meter. Okay. And that would be equal to, we know it, minus k multiplied by partial dt dx. Okay. The same thing now we do on this side. Okay. Again, use the differential approach. We would now say this is equal to qx plus partial ddx of qx of dx. And we will go through the whole thing and end up with a very, very long equation. Let me try on this side to write it down. And it looks like this. Rho multiplied by Cp multiplied by partial dt dt plus U multiplied by partial dt dx plus V multiplied by partial dt dy plus W multiplied by partial dt dz, okay, is equal to K multiplied by partial d2t dx squared plus partial d2t dy squared plus partial d2t dz squared, plus, and that's not the end, 2 times the viscosity multiplied by 2 times partial du dx squared plus partial dv dy squared plus partial dw dz squared, okay, plus the viscosity multiplied by 2 times partial du dy plus partial dv dx squared plus partial du dz plus partial dw dx squared plus partial dv dz plus partial w dy and the square of it. Okay, that's the equation, something like that. Maybe here and there I made a little bit of a mistake with an x or a y, doesn't matter. Just look at the equation. Now, what is different than the energy equation that we've considered up to now? The energy equation that we've used so far in the textbook of Sengel and Gujar doesn't look like that. So what is happening here? Okay. So what is happening here is that in the heat transfer cases that we've been considering, we've been looking at solids and stuff like that. We didn't look at flow or flow heat transfer, convective heat transfer. Okay. When we have that, then we can see that other terms are also now coming up. Now in terms of that control volume, we've just looked at the heat fluxes. But there's other work also that is being done. So it's not only the heat transfer, but there's other work. And that is work from viscous forces. Okay. Now previously we've written out some of the viscous forces, so comes in here again, and that is why that energy equation have much more terms than previously when we only looked at a body. Any questions on the energy equation? Okay. The detail of every step is not important. It's just about the framework of where it comes from that is important. Paragraph 4.7 is the stream function. Okay. Now the stream function is called psi. Okay. Psi. Okay. Now, before computers, this was the fundamentals of fluid mechanics. All fluid mechanics problems almost started with a stream function. Okay. Very, very important thing. And very powerful, but with limitations, and it's important that you know of the limitations. Okay, now the thing with this stream function is that it has the characteristics that it satisfies the continuity equation and the momentum equation. Okay. In one single variable. And that single variable is psi. So psi, that stream function, satisfies the continuity equation and the momentum equation. But in the derivation of it, assumptions were made. Firstly, that the flow should only be two-dimensional, so you cannot solve three-dimensional problems with it. Or, well, actually you can, it's an extension of it, but in terms of what we are going to do now, that assumption was made. And also that the density is constant and that we consider steady state flow. So if you make those assumptions, incompressible flow, steady state, two-dimensional, then there are many practical engineering problems that can be solved with a stream function. And many aeroplanes has been designed using this. Okay. And the stream function has the characteristic that you can calculate the velocity in the x direction by just deriving or calculating partial psi dy. And in the v direction it is equal to minus partial psi dx. Okay. Now these two equations, we can start with equation 1 again. It's equation 1. Okay. Sort of represents the behavior of a flow particle around a body. Okay. In wind tunnel experiments, you've seen it many times. You know, smoke is being generated, and when the smoke is being generated around a body, you can sort of understand or see how the flow would behave. And that is exactly what a stream function is, or a streamline. So if we have an aeroplane, okay, and that would now be a cross-section through an aeroplane wing, okay, and we would consider the flow over it, then typically that is what is going to happen. Okay. So if you think of yourself sitting on an air molecule, that is typically the path that would be followed if you are released from here. Okay. While if you're released from there, then that is the path that you're going to follow. Right, now these lines are actually values where the stream function is a constant. For example, 100. Okay. It is a constant. Okay. And this stream function would, for example, be 90. Okay. So the difference between the values would be the same. Okay. Now people who have worked with this a long time would look at this flow field and say, well, the velocities here are going to be low and the velocities there, here the velocity is going to be high and there it is going to be low. Okay. So if you think this of a channel and the flow is going through it, if the channel opens up, then the velocity would decrease. If the lines start going closer to each other, then the velocity would increase between the lines. Right. So just by looking at the flow field, you can already see where will the high velocities be and where will the low velocities be. The moment you know that, you know what the pressures will be, because that would just be the opposite. If the velocities are high, the pressures would be low. Very, very important for the design of an aeroplane wing. So anywhere here, if we are interested in what is the velocity there, okay, all we need to do is take this, get a representation of an equation through there, maybe a straight line, and then do the derivation, and then you can actually determine the velocities in the u direction and the v direction at any point. And again, if you would then take into consideration the Bernoulli equation, then you can also get the pressures at all the points. And with that, you can actually then get the pressure on this side and you can get the pressures on that side. And once you have that, you've got the lift on the aeroplane wing. But there was a big problem with that, always. Although people could do this, and it was brilliant work by the people at that time, and I'm going to show you some other examples just now. Okay. There was one problem. A big problem. What was that? Okay. When these assumptions were made, and I didn't write it down, the most important is the viscosity is also equal to 0. So in terms of the Euler equation, this comes from the Euler equation. Okay. So the result of that is because the viscosities are 0, it wasn't possible to get the drag on any body. You could get the lift forces, but not the drags. And that is why people started obviously doing wind tunnel work, and that is why wind tunnel work at that stage was so important. Okay. I see we are running out of time. We will continue with this with our next lecture. Thank you very much.